Greetings. The following is part of a series of lectures on cosmology. In this particular lecture, we will derive the Friedmann equations and explore some universes with single components, such as matter, radiation, and dark energy. The outline of this lecture is as follows. First, we will summarize what we have done in the last lecture. Then, we will proceed to derive the Friedmann equations. Next, we will write the Friedmann equations in terms of the density parameters. Afterwards, we will explore 4 types of single component universes. And finally, we will summarize the 4 types of single component universes using some plots. In the last lecture, we first mathematically formalized the notion of homogeneity and isotropy. Thereafter, we derived the Friedmann-Lemaitre-Robertson-Walker metric in the following form. And finally, we derived the possible spatial geometries under the condition of homogeneity and isotropy. We found that if k is greater than 0, then we have a closed universe with the following metric. Next, we found that if k equals 0, we have the flat universe with the flat Euclidean metric. And finally, if k is less than 0, we take the analytic continuation of the sine function, and we obtain the open universe with the following metric. There are also non-trivial topologies, but they will not be discussed as they are beyond the scope of this lecture. Now, let us discuss the Friedmann equations. The Friedmann equations are a set of equations in physical cosmology that govern the expansion of space in a homogeneous and isotropic models of the universe. To derive the Friedmann equations, we need to solve the Einstein field equations using the Friedmann-Lemaitre-Robertson-Walker metric. To do this, let us first write the Friedmann-Lemaitre-Robertson-Walker metric in an alternative form, namely the following. Like the last lecture, we will use the method of differential forms to compute the RTT component for pedagogical purposes. Then the rest will be listed out, as the same method can be used to obtain the other components of the Ricci tensor. To compute the Ricci tensor using differential forms, we first have to write the orthonormal bases. And the easiest orthonormal bases are as follows, where the hats denote the coordinate in orthonormal bases. Now, let the prime and overdot denote the derivative with respect to r and t respectively. Furthermore, taking the exterior derivative of the orthonormal bases yields the following. Now, we can use Cartan's first equation of structure to calculate the spin connections, and note that this equality is equal to 0 because in general relativity there is no torsion. And by inspection, the relevant spin connections are as follows. Now, recall that Cartan's second equation of structure is as follows, and recall that the Ricci tensor is defined in the following manner, and the Riemann tensor in orthonormal basis is related to the Ricci tensor in orthonormal basis in the following form. Thus, we only require the following derivatives of the following exterior derivatives of the spin connections, and by inspection we find that the Riemann tensors in orthonormal bases are as follows. And now, recall that the Riemann tensor in coordinate basis is related to the Riemann tensor in orthonormal basis in the following manner. And thus, the Ricci tensor RTT component is equal to -3 a dot dot over a. Listing out the other Ricci tensor components is as follows, and moreover, the Ricci scalar is the following. Now, let the energy momentum tensor be that of a perfect fluid, where P is the pressure, rho is the energy density, and U is the force velocity, which is defined in the following manner. Now, substituting the relevant Ricci tensors and scalars into the TT component of the Einstein field equation yields the following. Now, taking the trace of the Einstein field equation yields this, and thus equation 2.23 and 2.24 are collectively known as the Friedmann equations. These equations govern the dynamics of an expanding, homogeneous, and isotropic universe. Now, let us discuss the Friedmann equations in the context of the density parameters. The density parameter is defined as the ratio of the actual or observed density, rho, to the critical density of the Friedmann universe. The relation between the actual density and the critical density determines the overall geometry of the universe. The critical density, rho sub c, is found by setting lambda equals k equals 0. And moreover, if we set the Hubble parameter to be equal to a dot over a, we find that the critical density is as follows. Thus, the density parameter can be written in the following manner. If the density parameter is less than 1, there is too little matter to overcome the dark energy, and therefore the universe is open. If the density parameter is equal to 1, there is sufficient matter to counter the repulsive effects of the dark energy, and thus the universe is Euclidean flat. If omega is greater than 1, then there is too much matter, and thus the universe is closed. Subsequently, we will explore single component universes. From what we know, the universe consists of 4 major components: ordinary matter, dark matter, radiation, and dark energy. Although dark matter is much denser than ordinary matter, and dark matter contributes to the favor of the contraction of the universe, dark energy does not lead to the contraction of the universe, but rather the accelerated expansion. Now, to explore the single component universes, the Friedmann equations can be written in terms of the density parameters and the cosmic scale factors in the following manner, where h0 is the Hubble constant, omega 0, r is the radiation density today, omega 0, m is the matter density today, which include both dark and baryonic matter. Omega 0, k is the spatial curvature density today, and omega 0, lambda is the cosmological constant or vacuum density today. The first universe we will explore is an empty universe absent of matter, radiation, and dark energy. With this, omega 0, k is greater than omega 0, r, 0, m, and 0, lambda. Therefore, these parameters, omega 0, r, 0, m, omega, and 0, lambda can be set to 0, and omega 0, k can be set to 1. And from this, we obtain the following Friedmann equation. Therefore, solving the above differential equation, we yield the following, and we see that the cosmic scale factor is related to the time in a linear fashion, where here we have c as some constant of integration, but if we use the initial condition a0 equals 0, we find that c1 is equal to 0, and therefore a of t is equal to h0 t. The second universe we will explore is the matter-dominated universe. With this, omega 0, m is greater than all other parameters, such as omega 0, k, 0, r, and 0, lambda. Therefore, the density parameters omega 0, r, 0, k, and 0, lambda can be set to 0, and the density parameter omega 0, m can be set to 1. And from this, we obtain the following Friedmann equation. Solving the above differential equation yields the following. And as we can see that a is proportional to t to the 2/3. And we add a constant here to compensate, which is the age of the universe. The third universe we will explore is the radiation-dominated universe. With this, omega 0, r is greater than all other parameters, such as omega 0, k, 0, m, and 0, lambda. And therefore, the other parameters, omega 0, m, 0, k, 0, lambda, can be set to 0, and omega 0, r can be set to 1. And from this, we obtain the following Friedmann equation. And solving the above differential equation, we obtain the following. Here, a is proportional to t to the half, and t0 is, again, the age of the universe. The final universe we will explore is the lambda-dominated universe, and this is a little bit different because it's not related as to t as a power law, but instead as an exponential. With this, we can find this in the subsequently. With this, omega 0 comma lambda is greater than all other density parameters, such as 0 comma k, 0 comma m, and 0 comma r. Therefore, these other parameters, omega 0 comma m, 0 comma k, and 0 comma r is set to 0, and omega 0 comma lambda is set to 1. And from this, we find the following Friedmann equation. And solving the above differential equation, and using the fact that the second derivative with respect to time is positive, we find that the cosmic scale factor is related to time as an exponential function, where a naught is some constant that represents some initial cosmic scale factor at t equals 0. Now we can see from this plot. To summarize, we plot the cosmic scale factor a versus some conformal factor times time. Now notice that in the plot, the plot has been normalized to have the same scale factor and expansion rate in the current epoch for all cases shown. As we can see, the cosmic scale factor increases more rapidly with time for the lambda only universe compared to the radiation and matter only dominated universe. Moreover, the slope of the matter only universe and the radiation only universe is less steep than that of the empty universe. This indicates that the radiation and matter hinders the universe's ability to expand. That is all for this lecture, and I hope you have learned something, and see you in the next lecture. Thank you.